Establishing a mass gap for pure Yang-Mills theory on four-dimensional flat spacetime remains one of the defining unsolved problems in modern physics. Proving a strictly positive lower bound for the energy spectrum on an infinite plane presents immense analytical difficulties. Shifting the domain to a compact spatial slice alters the boundary conditions, transitioning the problem from an infinite continuum to a manifold with finite volume. Confining the theory to a finite volume naturally discretizes the energy spectrum. For this proof, we constrain the spatial slice to a specific target, the Poincare homology sphere, the unique homology 3-sphere with a finite, non-trivial fundamental group. This geometry provides a unique advantage. Its fundamental group, the binary icosahedral group, is the largest finite subgroup of SU2, directly linking spatial topology to the internal symmetries of the gauge group. This link allows us to resolve the spectral gap by evaluating three distinct layers of the theory: the Riemannian geometry of the metric, the topological isolation of the vacua, the algebraic representation of the fluctuations. Developing the theory on a compact 3-manifold allows us to evaluate the mass gap within a strictly defined geometric and topological system. We begin with the geometry inherited from the parent space. The homology sphere inherits the round metric and positive curvature of a standard 3-sphere of radius r. The gauge covariant Hodge-Laplacian R1 forms decomposes via the Weizenbach identity into the connection Laplacian, the Ricci tensor, and a curvature endomorphism. When evaluating fluctuations around a flat connection, the field strength vanishes. This causes the curvature endomorphism to equal 0. The connection Laplacian term is inherently non-negative. This leaves the Ricci tensor, which provides a uniform, constant positive contribution of 2 over r squared. Regardless of the vacuum state or the specific topology, the positive curvature of the manifold enforces a universal floor. No physical gauge fluctuation can possess an energy lower than 2 over r squared. Beyond the curvature of the metric, the spectrum is constrained by the specific vacuum states the theory can occupy. Henri Poincaré established the foundations of homology and Betti numbers, the topological invariants that describe the dimensional structure of a space. Because the Poincare homology sphere has a vanishing first Betti number, there are no harmonic 1 forms. This eliminates 0 eigenvalue solutions by default. This defines the flat connection moduli space, the set of homomorphisms from the fundamental group 2I into the gauge group SU2, modulo conjugation. For the binary icosahedral group, this mapping yields 3 isolated points: the trivial connection, the standard embedding, and its Galois conjugate. For the non-trivial flat connections, their irreducible nature means their first cohomology group with local coefficients is 0. Mathematically, this vanishing cohomology implies a vanishing Zariski tangent space at those vacua. Without tangent space dimensions, there are no continuous parameters to create vacuum degeneracy. The states are topologically isolated, preventing the generation of massless modes. While the curvature sets the floor and the topology isolates the vacua, calculating the exact eigenvalues requires evaluating the symmetry of the fluctuations. This equation shows the energy levels for divergence-free 1 forms on the parent 3-sphere. These are indexed by an integer level k. Not all these modes exist on the quotient manifold. The physical fluctuations must survive the left multiplication action of the binary icosahedral group. This is the condition of twisted equivariance. A mode only survives if it transforms under the adjoint representation of the specific vacuum. To find the spectral gap at each vacuum, we must identify the lowest integer level k, where the vacuum's adjoint representation appears in the manifold's allowed spin representations. We map these representations using the Mackay correspondence. For the binary icosahedral group, this restriction is governed by the structure of the extended affine E8 Dinkin diagram. Each node represents an irreducible representation. The standard vacuum corresponds to the 3A representation at node R2, while the Gala vacuum corresponds to 3B at node R8. We evaluate the levels k incrementally to see when these nodes first activate mathematically. At level k equals 1, the restriction yields the 3A representation. Since 3A appears immediately, the standard vacuum possesses a mode at the very first coaxact level. Plugging k equals 1 into our eigenvalue formula yields a gap of 4 over r squared. The Galois vacuum, however, requires the 3b representation. At k equals 1, 3b is absent. The representation remains absent through levels 2, 3, and 4. The 3b representation finally appears at level k equals 5. Substituting k equals 5 into the spectrum formula results in an energy level of 36 over r squared. The icosahedral symmetry of the space filters out the first 4 coaxact levels, resulting in a 9-fold energy enhancement at the Galois vacuum, a direct consequence of its graph distance on the E8 lattice. The final aggregate result for the theory is a spectral gap of 4 over r squared, set by the trivial and standard vacuum sectors. Breaking this result down reveals where the physics is determined by the metric versus the topology. The existence of the gap, the isolation of the 3 vacua, and a 9-fold Galois enhancement are topological constants. They remain invariant regardless of the metric. The numerical eigenvalues and the 2 over r squared floor, however, are entirely metric dependent, scaling with the radius of the sphere. If the radius r approaches infinity, returning the manifold to flat space, the gap vanishes. While a mass gap on infinite flat spacetime remains unproven, on the Poincare homology sphere, the geometry, topology, and algebraic symmetries interlock to provide an exact, rigorous solution.